In our previous video, we spoke about protocols that were useful for end users. They were protocols that were intended to let the user send emails or to let the user browse the web. Those are the reasons why we built networks, to provide users with that functionality. So that is aptly called the application layer. However, we also need some applications to manage the network, to work with the network that we are dealing with. And these are the protocols that we will talk about in this video and those that follow about the application layer. Our first example is the DNS, the domain name system. Now, the domain name system is not really a protocol. It is a protocol suite, entire set of protocols, and we will encounter some of them, possibly not even all of them, as we go along. However, they are application layer protocols, and we will treat them as if they were one for most of our discussion. Now, to get to the DNS, one has to think a little bit about the history of the internet. One also has to think about the operation of machines. If you, for example, consider the telephone network, then you know that every telephone has a number, and if you want to reach that telephone, you would just dial the number. Computers similarly prefer to work with addresses, numeric addresses, numbers. And if you want to reach a specific computer, if you want your message to be routed to a specific computer, you have to provide the address at which this computer is situated, or with which this computer is associated. Now, if you have a tiny number of numbers, then it's not a problem at all. You may even remember them. But as you probably know nowadays, even with cell phones, what you tend to do is have all your contacts in a directory or a contacts list, and what you have in there is the name of your contact and their telephone number. And you hardly ever refer to the telephone number. You just work in terms of the name. It's fine for telephones to have such a little telephone directory because you probably have only a fixed amount of people that you want to call regularly. However, on the internet, there are lots of reasons why you may want to talk to machines that you've never previously talked to, and you need to be able to convert their names to their addresses. Many years ago, you already saw that the internet consisted of 5 hosts, back in 1969 as ARPANET. But so in that case, you probably could remember those 5 numbers if you really had to. But as the internet grew, they realized that they needed something better. And the something better that they installed was a file which contained all the names and addresses of computers on the internet. And that file still exists on modern-day computers. If you look at your Unix machine or Linux machine, you will see in etc/hosts that you have a remnant of that file. And even on Windows, if you go to the appropriate directory, there it is. And check your cell phone. It may even be there. As the internet grew, systems had to regularly download this file with all the names and numbers. And the internet grew and grew and grew, and at some point it just became impossible for every machine to download this file every day. It was a huge file. It would take days to download it if you were still using that system, and the internet would have changed by the time you would have downloaded the file anyway. So that solution was simply not sustainable. And in its place, they wanted a simple system that would enable one to work in a more distributed manner. So they wanted to build a distributed database. And the resulting system was the DNS, the domain name system. The domain name system is an interesting system to study from a logical perspective, from a technical perspective, how it works. The DNS is also a perfect example to illustrate a number of the design concepts that underlie the Internet. One of these concepts was the notion of local autonomy. The way in which you will set up your own name server is as follows. You will create a little file, and that file will essentially contain all your computer's names and all their addresses, and some other information that we will eventually talk about. Then you will run a server, and anybody who wants to can query that server, and if they give the server a name of one of your computers, then the server will return the address. And you can add as many computers as you want to. You can change their names as frequently as you want to. You can change it by the minute, or you can leave it without touching it for years. You have the local power. You also have other powers that we will eventually talk about. Another of the design principles that we spoke about was the notion of redundancy, so that the network does not have a single point of failure. So you will soon enough see that with name servers, we will always replicate them. You will have at least 2 name servers, because if your name server is down, then people cannot access your computers. So if you have 2, then at the very least, they can try the other one. And the other one will hopefully be on a very different network than the first one, so that if the first one is on a network that is not accessible, the second one will be accessible. But we'll talk about redundancy and fault tolerance later on. In terms of a user using your name server, that happens transparently. Remember that the ordinary user is sitting in front of a computer, they're browsing the web, and they enter some URL, and that URL contains the name of, let's say, your computer. And their system will eventually query your name server, and it will get the address, and once it has done that, it will be able to send requests to your machines. Exactly how it gets to your name server is a very interesting story. That's really where the fun starts. But in terms of the basic functionality of a name server, that's quite simple. You simply look at this file that we will soon call the zone file. You look up the name that is being queried, see what the associated address is, and that is what you return. Also, think about your browser as the software that this other user is using. We already said that this software interfaces with a number of application protocols. It may interface with HTTP in order to serve web requests. It may interface with FTP for file transfer protocol interactions. And it will also interface with the DNS, because it needs to take this name and get it converted to a number, to an address. So your browser, even though it's not something you necessarily think that you need to be able to do, the network knows it needs to do this, and the browser will therefore have an application layer interface that will talk to DNS servers in order to get this name translated into an address. Such name translation, by the way, is known as name resolution, and a lot of what follows will be about the process of name resolution. As noted, the DNS is a hierarchical system, a tree. What you are looking at on the screen right now is a microscopic depiction of a part of this tree. Now, like any tree, this tree starts at the root, and that root doesn't really have a name, The lambda that you see there is intended to indicate the empty string. So you can't really write down its name, but we will see just now why it is important to have something like that. Moving on from that, this tree has a number of children, and these are known as the so-called top-level domains. And top-level domains are the ones that you are probably familiar with, at least with some of them. One of the examples that you have certainly used millions of times is the .com domain, which sits right beneath the root. We are scrolling through these top-level domains, and you will see that they fit into three categories, or into one of three categories. The first couple are the so-called generic top-level domains, Gtlds. And they are generic in the sense that they existed on the internet from very early on, and they were essentially open for anyone to use. However, there were a couple of special ones, and even though they were always described as generic, they were not really generic, such as .mol and .gov, which are specifically reserved for the American government and the American military. So I guess they could have put in those names for themselves without having to explain why they did it. It's their network, or was their network. As we move down the list, we encounter the country code top-level domains, Cctlds, if we use the acronym. The country code top-level domains are those that have been assigned to every country in the world. In each case, it is a two-letter indication of the country, and the one that is of particular interest for us is the .za top-level domain, which is used for South Africa. Many people ask, why are we not using .sa? Well, .sa is Saudi Arabia, and we got the .za. With only two letters, you cannot give everybody exactly what they would like. Moving down this list, through the country code top-level domains, we reach the sponsored top-level domains, or STLDs. The sponsored top-level domains are those that were put into place because someone wanted them for some particular reason. And sometimes they are for a specific group of users. Sometimes you need some qualifications to have a space in them. In other cases, they are open, they are just alternatives, because the domain name system became so congested that we did need alternatives. One of the tools that we will use to query the name servers is nslookup. nslookup is available on all your popular operating systems. Some people will say that they hate nslookup and they prefer dig. For our purposes, nslookup is good enough, and we will use nslookup. If you prefer dig, go ahead by all means and use dig. As we noted earlier, your interfaces with the name servers are often built into other software. In other words, in your browser, you have the ability to query the name system to get names resolved. nslookup is a simple utility that gives you the ability to do such lookups on your own. It has no real purpose in the network apart from giving you the ability to perform such lookups. There are two main ways in which you can use nslookup. You can go to a command prompt terminal and you can enter nslookup space, even more spaces, the name that you want to be resolved, hit enter, and nslookup will do that for you and provide you with the answer. Alternatively, and that's the way in which we are going to use nslookup, you will type nslookup, hit enter, and then you will be in a little nslookup shell. You can get out of it by simply pressing Ctrl-C or break, but while you are in that shell, you can enter various commands. If you enter a domain name, it will resolve the name for you and provide the address, but that's not what we're going to do immediately. Let's try something different. When you enter the nslookup command, it will probably tell you which default server it is using. We're not going to worry about that at the moment. And we are in the shell where it displays this greater than sign that prompts us to enter something. What I'm going to do here is to say set type is equal to NS. The reason why I'm doing this is because I want to establish which name servers are listed in the zone file for the root domain. So let us enter just a full stop, that is the name that we want to have resolved, and then see what we get as a response. And what we get as a response are 13 entries, 13 root name servers, and they are simply called a.rootservers.net and b.rootservers.net and c.rootservers.net and so on. And those 13 are the ones that can resolve top-level domains. So if they were to fail, all 13 of them were to fail, then none of the internet would be accessible. And hence they decided, let's create a fairly large number of these name servers, 13. Don't know whether the superstitious would think that 13 was a good number to ensure fault tolerance, but let's leave it there. And they are telling us that those 13 servers are available. So if you want to know something about the .com domain, we can simply ask that root name server. Similarly, if we want to know something about the .za domain, we can simply ask that root name server, any one of them in fact, because they all replicate what the others have. And they are located throughout the world, originally many in the United States and Europe. But over time, those 13 have also been replicated so that those are not really single machines anymore. And you will find that something like f.rootservers.net actually is a computer that is situated somewhere in the United States, somewhere in South Africa, and somewhere in a couple of other places in the world. So even if you were to take out one of the f.rootservers.net, then others will still exist with that very same name. And they sort of broken the routing algorithm a little bit so that your requests will be routed to the nearest root name server to you, depending on which one you've selected, obviously, A, B, C, D, and so on. So many more than 13 root name servers actually existing in the world. Now, suppose that we want to find out more about the ZA domain. Then we can type in ZA, and it should resolve that for us. Remember that we are still in the setting where we set it to look for name servers. So that's arguably the most important thing right now. We want to know how to move to the ZA domain. And then once we are in the ZA domain, we want to know how to move to other entities in the ZA domain. So what I'm going to do here is I'm going to enter ZA. But that presents a challenge. ZA on its own may be a relative name. If I'm talking about the ZA domain in a South African context, everybody knows what it is. But here I'm talking to some server, and it can be anything. So what I really have to enter is a fully qualified domain name. And a fully qualified domain name will have all the parts and all the parts will be separated by full stops. Now what we have at the moment is the empty name of the root, and then a full stop, and then ZA. So the proper way to enter this is ZA full stop. I'm going to do the query like this using the current name server, but then once we've done that, we will talk about the way in which we really should do this. So let's just find who the name servers for the ZA domain is, and then we will talk about how the process works at a lower level. It is arguably worth trying our other two options, entering ZA without any full stop or entering .za, and you will see that both of them fail. Before we explore further using nslookup, let us return to that picture, that diagram of the DNS that we looked at a little bit earlier. What you will hopefully realize at this stage is that the lines that we are looking at that start at the root node and then go towards the other nodes are the NS records. They are the pointers. So in this tree structure, every NS entry is a pointer to another server where you can perform lookups. To make matters a bit more specific, let us look at some of these links, and more specifically, these links happen to be called delegations. So what ICANN did when they created the .mil top-level domain is that they delegated authority for that domain to the American military. And the American military looked at the situation, and they decided, well, let's create a subdomain, and we're going to give that for the army. And then another subdomain, and we'll give that to the Air Force. Another one, and we'll give that to the Navy, and so on. It could also, without using the subdomains, have a couple of computers that are directly addressed. But the important point that I am making at this stage is that the military has complete control over that domain, and they can decide how to operate it, what to do with it. Now let us take another example. If we follow the path to the .com top-level domain, then you will realize that there's very little control that can be exercised over the .com domain. Everyone who wants a .com domain can go and register it if it's available, and if there is nothing preventing them from registering it, then they can simply go and register it. So what you need in that particular case is the equivalent of a zone file, and that zone file will form part of a so-called registry. We will hardly ever talk about a zone file in such a context. We will rather talk about a registry, and this registry will, amongst others, contain details of the person who registered this particular domain until when it has been paid for, what the person's address is, and so on and so on. We will look at the contents of the registry in a bit more detail in a moment or two. The point that I'm making is, in that .com domain, top-level domain, anybody who wants to can go and register a name, and it's fine. There are a few exceptions. For example, the second-level domain example in .com has been reserved by an RFC for use in examples, so nobody can register that. The problem with the .com top-level domain is that so many organizations and individuals have registered names in that domain that it has become rather hard to find an appropriate subdomain, second-level domain in it. Let's now follow the path that we started exploring with nslookup a little bit earlier. From the country code top-level domain .za, we know that everything in the .za domain has to be administered by South Africa. That's the principle of local autonomy. In the case of the .mil, the US military can administer everything in that, but they already have a command structure, so it's not a problem. But who takes the responsibility for administration of the .za top-level domain? In other words, to whom is authority to make decisions about the .za domain delegated? Historically, many years ago, it didn't really matter. It was an academic network and people played a little bit on it and so on. So way back, a couple of companies, handful, half a dozen companies, registered names on the second level in the ZA domain, and some of them still have that second level domain. But over time, South Africa decided that we were going to divide our top-level domain into about 20 or so second-level domains. The organization that was eventually established after the fact, this is after the internet has become important from a commercial perspective and a security perspective and so on, is an organization known as ZADNA. ZADNA, the ZA Domain Name Authority. ZADNA has the authority to make decisions about the .za top-level domain. Amongst others, this includes deciding who is allowed to register a second-level domain and, in fact, to add and remove second-level domains as they deem appropriate. As you probably know already, in South Africa we have a CO second level domain within the .za top level domain, and it is used pretty much like the .com domain, except that it is attached to South Africa in particular. So anybody can go and register a name within it, businesses, individuals. They need not be South Africans. There are hardly any restrictions on the registration of third-level domains in the COZA domain space. We also have the AC.za domain, and that is used for academic institutions, such as universities. The academic services, in general, the internet services for academic institutions in South Africa are provided by an ISP that is known as TENET, the Tertiary Education Network ISP. And what they do is provide connectivity for such institutions, but they also act as the so-called registrar for the ACZA domain. In other words, they are the people who not only operate the registry, the zone file plus additional information for the ACZA second level domain, but they also act as the party who adds other organizations, particular universities and technikons and research institutions into the ACZA domain. So just to recap, the registry is essentially a zone file with additional information such as addresses and payments and so on. The registrar is the party who is able to add names to that registry and remove names from the registry. And then there's also the registrant, the party whose information has been entered into the registry as the owner of a particular domain in that registry. We also have the gov.za second level domain, and that has been given to the South African government. And clearly they can do with it whatever they want. And they've created subdomains for various government departments and other entities in government, but they determine the rules for that domain. There are some domains in South Africa that are very exclusive. You need to be a member of some organization to be able to get an entry into such a subdomain. And then, as we've noted previously, the co.za domain and also the org.za domain, and in fact a couple of others, are very, very open. To take the example a little bit further, you can see that one of my domains, mo.co.za, is also in that diagram. And what you can see is that the CO registry delegates authority to me to run that particular domain. So I have DNS servers in place. Yes, they're provided by an ISP. It's no big deal. When you register a domain name, they provide the name servers as part of the package. But those point to a DNS file, to a DNS server, in fact, where I have access to the DNS file, and or more specifically to the zone file. And what I can do in that file is to add all sorts of addresses, names for my machines, and add their addresses next to them. I can also create subdomains within that domain. In fact, there are a couple of subdomains that exist within that subdomain. And I can either operate them myself, or I can even allow someone else to operate them. So I can, in a sense, almost act like a registry if I wanted to give other parties subdomains within my domain. So whatever I call the machines in my domain, it's up to me. It's local autonomy at work again. Yet another example, in the AC entry in the ZA domain, you will see that it has pointers to the various universities, and amongst others, it points to the University of Pretoria. And the University of Pretoria has decided to put quite a number of computers in their particular subdomain. So there is a computer in principle. Obviously, nowadays, many of these things are virtual computers that are in the cloud or whatever. But in principle, they have a computer that is called www, and the address of that particular machine can be found in their zone file. And to get to their zone file, one merely has to query the AC zone file. As always, there will be multiple name servers that will point to the university's name servers, and the university will have multiple name servers that will have information about the university's infrastructure. So redundancy throughout again. Just to illustrate the notion of local autonomy a little bit further, if we follow the link for Australia, you can see that Australia did not follow this convention of having a .co and a .ac and so on as second level domains. Australia rather decided that they want a .com as their second level for commercial enterprises and individual use, pretty similar to the COZA. So a similar entity, if you have a business X in Australia, it will register, if the name is available, x.com.au. As another example, if we follow the link for Germany, .de, Deutschland, then you can see that Germany decided not to have specific second-level domains. So we in South Africa have a .co and a .ac and so on, examples that are often shared with the English-speaking world. In Germany, they decided, possibly because English is not the common language used in Germany, to enable organizations to create names in their domain name system. So you'll find instances like universities very often have uni dash and then their name. The example that you can see there is Uni Heidelberg, and commercial companies will also register their names and so on. It means that there is more competition because there's no natural subdivision, but it does have its other advantages. Just for the sake of completeness, if you look at the University of Heidelberg, you will see that they have Informatik as one of their servers. In Europe, informatics, or in Germany then specifically Informatik, or in the Netherlands Informatica, is the term that is used for what is known as computer science in other places in the world. So Informatik would be their computer science department, the equivalent of our computer science departments in South Africa. And very often they don't really have something that is equivalent to the informatics departments that you tend to find in South Africa. Let's follow one final example in this diagram before we get back to the operation of the system. And this deals with the various sponsored top-level domains. It's a fairly recent development on the internet to create new sponsored top-level domains. It's where a party says, I want to register a top-level domain on behalf of a specific industry or on behalf of a specific place and so on. So there, as one example, you can see .joburg. .joburg is sponsored by ZATNA. So the ZA domain name authority is the organization who operates it, and they determine the rules of who is allowed to register subdomains within it. As one of the interesting examples, you can see that Chris Hani Baragwanath Hospital is registered within this sponsored top-level domain. Whether that is a good choice or not, I'm not quite sure, because I dare you to go to a web browser now and type in the URL Chris Hani Baragwanath Hospital.joburg and see whether you spell it right, and then think about the situation where you have to enter that in a hurry when it is an emergency. However, I should note that that particular hospital has a number of URLs that all point to the same content eventually. So they may have a reasonable name that you can just enter very quickly in case of an emergency. Or I guess you can always just search for it using your favorite search engine. But hopefully at least a few of you are feeling somewhat uneasy about our description of the DNS thus far. The problem is, if one has a tree and you have all these nice links going from the higher level domains to the lower level domains, how do you get to the root of the tree? Because if you can't start somewhere, it is impossible to traverse the tree. And the answer is a very simple answer, really. The 13 root name servers that we encountered earlier have been in place and have not changed their addresses and will not change their addresses for a long, long time. Therefore, any name server that needs to know where the root name servers are will have that information built into it. Will be part of a configuration file or something, but it will work under the assumption, which will happen to be correct, that those addresses will not change. Hence, it is shared knowledge throughout the networking community what the addresses of these 30 name servers are, and once you can find one of them, you can find any one of them. So let us now do a proper name server lookup. What we've done thus far was not a proper lookup in the sense that we did not follow the correct recipe. It is the correct way of doing it in general, but if you want to do it in the way that the name servers work, in the way that the DNS works, then we have to change our strategy. And let's do that. It's fairly simple, in fact. For this example, I want to determine the address of a specific node, specific machine. Let's say we want to determine the address of www.mo.org.za. So that's the purpose of this whole demo. And what we're going to do here is go into nslookup. You may recognize that server because we've seen it in previous examples. I'll explain its significance in a moment or two. We have just entered nslookup, so it will automatically do address lookups. However, to be certain, we might as well say set type is equal A. It's not necessary, but it makes it very clear what we are looking for. So to reiterate, what we want to do is we want to determine the address of that particular machine. And if I now hit enter, because we are using that server, it will provide me with an answer. But it will do a lot of processing internally. And for this example, I really want to do the processing by hand. So let's hit enter so that we get an answer, and that is the answer that we expect to see at the end of this demonstration. However, what we are going to do is to take the long route. To take the long route, I need the name, or I need the address of a root name server. Given that we are still looking for type A records, let's just ask it what the address of a.rootservers.net is. So normally this would be assumed to be a known number because it is one of the known root name servers. For this example, we looked it up, which is fine. Let's now change servers. So I'm going to say the server that should be used henceforth is the one that we've just picked up. Hit enter and it tells us that it is indeed now looking at a.rootservers.net. That particular root server, like any other one, will only provide us with name server pointers to top level domains. So if I were going to ask it about any other domain, we will just get a response that it is not permitted, or some other response that will try and point us in the right direction. We know we are dealing with a root name server, and I'm going to say that I know that that can tell me about name services, particularly of top-level domains. If I ask it for a top-level domain, then it will need a full stop as previously, and hitting enter should provide us with information about the name servers for the ZA top-level domain. So let us pick one of these IPv4 addresses. Let's say that one. Copy it and change our server to that particular address. That is a server that will hopefully be able to answer queries about the ZA domain. There is some suggestion in the name of the machine that it is indeed a name server for ZA. Our hope is to find a pointer for org.za. So we are still set to do nslookups, and let's see what we get for org.za. And there we get quite a couple of name servers for org.za. The challenge is that we are generally supplied with names that need to be resolved. These are symbolic names, fully qualified domain names. So we may have to start right at the root again and find a way to resolve, let's say, that address. So go from the root to com to iAfrica and then to NS4 before we even know what the org name server is. But fortunately in this particular case, we have been supplied with one address. It is the address of that one. So we can use that, and that one is indeed a name server for org.za. So let's copy that and then say server and set it to this new value. With this new value, we should be able to look into org.za, and the one for our particular example is mo.org.za. Hit enter, and we get name servers that are set up, that are configured, 4 of them for this particular domain. But in this case, we are less fortunate because all of these name servers that we get are fully qualified domain names. In other words, to move any further from what we've just received would require us to go back to the root server and then find a pointer to either net or com and then resolve it from there. So I'm not going to repeat this entire process. I'm going to take a little bit of a shortcut. Rather than going back and resolving these from the root until we get to the name, I'm going to use my faithful old server that I've used previously to just convert one of these names for me to an address. So if I want an address, then I need to say set type is equal to A. So it will do address lookups, not pointer lookups. And then I can say, let's pick that one, that I want to resolve that name. And what I'm going to do here is say resolve that name for me, but don't try and use the one where we are at the moment. This is one that is supposed to resolve names that are in that domain. And at this stage, I want an OH resolution in the .NET domain. So I'm going to say, just look that up for me and use that name server that we used right at the beginning and there we get the address. So what this means is that that name server that we are looking at there, which is willing to resolve names for that domain, is actually at this address. So let's copy it and change our server to this address. And we, at this stage, are at the position where we followed the pointer from the root to ZA, to org, to MO, and remember that the machine that we want to look up is www.mo.org.za. So we are indeed now interested in no longer following a pointer, but we want the address of that machine. So our last setting was to set the type equal to A. So this is not necessary, but to emphasize the point that we want an address now, we follow the pointer to the leaf, and once we get to the leaf, we want to find an address. So doing that, as I said, unnecessarily. And now I'm going to ask for www.mo.org.za, hit enter, and there is our final answer, which you can go back and compare to the one that we got originally. In fact, we can quickly do it if I ask for that name to be resolved, but not on the default server, but using the server that we started with initially. Then we in fact get the same value, so this lookup is correct. To reiterate what we've just done, we resolved a domain name, a fully qualified domain name, by working through all the layers that were necessary, starting at the root, going to the name servers for the top level domains, and so on, until we eventually got to the server for the particular domain in which we were interested. This domain, mo.org.za, we found its name servers, and then we could look up the address of the host in its name server. In order to perform that very last step, we were given a couple of name servers, 4 of them in fact, for our domain, but they were all specified as fully qualified domain names. And remember that what we did there was, rather than go through the entire process from the root again, we just quickly used that name server at 10.1.1.1. The difference is the process that we've been following is known as iterative name resolution. That's where you start at the root, and once you get the name of the server or address of the server that can help you to move one level up, you move one level up and you ask that server and you move one level up and so on. That's iterative. However, the server that I've also been using, the one installed at 10.1.1.1, performs recursive name resolution. And in order to do recursive name resolution, or what it means by doing recursive name resolution, is that it goes through all the steps that one needs to go through if you were doing it iteratively. So I can just simply give it the domain name, the fully qualified domain name, entire name. I don't have to think about root name servers or anything. It will do that on my behalf. Now, with our intention in this module of letting you understand how the process works, it is important that you are able to go through the process in an iterative manner. However, in practice, what you will do when you need to resolve a name, and in fact what we've said is in practice very often you won't even know it because it will be built into the browser and it will query the name server, most probably a recursive server, and the recursive server will simply do all of this iterative work behind the scenes. But if you ever wanted to do a name lookup with something like nslookup, then you would use a recursive server in the real world. Our intention, again, to repeat, is to understand what's going on, and therefore we need to understand this iterative process. If you are using an ISP, the ISP would probably provide you with a recursive name server, so you don't even have to worry about root name servers or skipping through the various layers until you get to your final answer. Same if you are in most companies or at universities and so on, the name server that would be provided as a default would be one that does the work recursively. So there would be no need for you to know anything about the details, the internal operation. In fact, there are a couple of name servers that have become rather popular on the internet that will also do this work for you, recursively, on your behalf. You ask it just about a name, and it will traverse the entire tree as necessary and resolve the name for you. Before we look at these, let's just quickly make the following remark. Typical name servers will cache a value once it knows it for a while. Therefore, if a server has looked up, let's say, what is the name server for .com queries, then it will not go back for the next while to the root server to ask it, where can I find information about com servers? Because it already knows that. It will work from its cached address. And the same is true for the higher levels as you go deeper and deeper into a name. If you use it repeatedly, it will just work from the cache. And if you think about the typical organizational name server, then it will cache all the names that are used by all the people, and all the people are highly likely to use, let's say, at the very least, .com or .edu every once in a while. So those will be cached. And because of this caching, it is hardly ever necessary for these name servers to go back to the root servers. So it is not the case that for every name resolution that you perform, a root server will be queried. Root servers will only be queried every once in a while when a value for, let's say, the .com level, the .com domain, becomes stale. Let's now just quickly look at these other name servers that, as I've said, are becoming quite popular and are in many cases used as alternatives to the name servers that are provided to you by your ISP or even your organization. Before we get to the name resolution services that we promised to discuss, let's quickly show you one additional feature of nslookup that we haven't seen thus far. You have seen us entering a name such as a.rootservers.net, and you've seen a response that was provided. Now, if we copy this response, where is the address, then we can enter the address and it will tell us what name is associated with this address. Now, in this particular example, we are fortunate in the sense that the name that we get back is exactly the name that we started out with. Nowadays, many servers are, for example, co-located, and you may map a fully qualified domain name to an IP address, but when you reverse the process, when you go from an IP address back to the name, there are so many web servers on that machine that you will very often get the name of the actual computer that is hosting all of those web servers. So you will find information that does not map back entirely as expected. The reason why I've just mentioned this is because one of the best known recursive name resolution services on the internet nowadays is arguably the one provided by Google at address 8.8.8.8. What I can do with that address is to enter it just like that, and it should do a reverse lookup for us, and you will see that the result that we get back is dns.google. Now, if you've not realized it before, Google is a sponsored TLD. In fact, you can also do a forward lookup on this. If you say dns.google, then you will see that there are actually 2 of these services that are provided, and you can use either one, or if you need 2, you can use both of them. This has become very popular, especially as users switch between service providers and they don't want to be stuck with a specific service provider. Then that is one of the reasons why they may want to use that one rather than the one provided by their ISP. The second example that we need to talk about is the name server sitting at the address 1.1.1.1, and we can also find its name. Now that is a particularly interesting name. Clearly, .1 is another one of these sponsored top-level domains, and they've taken it all the way to get to 4 ones. This is one that is, amongst others, provided by Cloudflare and Appnik, about which we will talk much later in this module, is a co-sponsor of that particular service. One of the benefits that they promise is privacy. If you are serving, let's say, the web, every web request you send out will cause a DNS lookup, and if those DNS lookups are cached at all, then it means people know exactly what you are browsing, even if things are encrypted. Whether you can trust this particular company to indeed provide you with privacy is a question that I'm not going to try and answer. There is also the additional benefit that is promised by companies like these or services like these, is that they will often try to filter out adult content. So if you provide a name that is known to have something that is unwanted or that is even illegal behind it, it will simply not resolve the name for you. So it may be worth considering if you don't want to accidentally stumble onto one of those sites, or also where there are minors who may access a system. Then you can look at the promises that are made by providers such as these and decide whether they are indeed fulfilling that promise. So I'm not trying to sell them, I'm just trying to say what sort of a promise they make. There is yet another such service that makes very similar promises. That one doesn't have an easy address to remember, so you have to look it up if you don't have it written down somewhere, and that is opendns.com. There you can see the address. This particular service forms part of Cisco. So a couple of major players who are beginning to provide these recursive name servers that you can decide to use. The latter two tend to advertise privacy and even adult content filtering. The Google one, I have not seen any particular claims made about it, but we know that Google is particularly interested in tracking what people are doing to learn more about them. So it may be part of their data gathering operations. On the other hand, they may be making similar promises about privacy and filtering of adult content. I just don't know. One of the other questions that one often gets asked when talking about domains and IP addresses is whether one is able to determine to whom a specific domain or domain name belongs, or even to whom a specific IP address belongs. We will talk about IP addresses much later when we get to layer 3, but in the meantime we can provide some insight into ownership of domains and see what we can learn about them, again using easy to use, very available tools. In order to establish who owns a domain is in principle rather simple. There is a whois command, and this whois is unfortunately not available in Windows, so you will have to move to one of the other platforms that are popular in order to use it. And whois can be used with a domain name, and it can also be used with an IP address. We're not going to look at the IP address details now, but let's look at the domain name. So if I, for example, say whoisgoogle.com, then I get rather long terms of use, but what you did not see that scrolled away is google.com there. There is the updated time and date and so on. There are some contact details, and there you can see some information about the server they use and so on. So a pretty comprehensive list of information. To take this one step further, let's clear the screen so we can get rid of all of this. And we ask whois, and we use the domain that we analyzed a little bit earlier, mo.org.za, and click enter, and then you will see that we get a bunch of information. There's the domain name, and there's no particular whois server for this registrar. There is the details of the registrar and so on. But the moment when you get to things like the registrant, the name of the person who registered this domain, you can see that that has been redacted. And the organization is private, and the street where this person lives is redacted, and the city where this person resides is redacted, but this person happens to be in Gauteng, and this person happens to be in South Africa. The telephone number of this person has been redacted, and so on. Now, the reason for all of this reduction is because this was a prime source for spammers to get email addresses, for marketeers to get email addresses, and so on. And in the end, it just became too much, and it all was redacted. And I guess you can possibly guess who the owner is and why the owner doesn't want the students to be able to easily find his house address. So it may be a really good reason for getting this all redacted. It just makes life easier for some lecturers. So in a nutshell then, the whois command enables you to get such information if it's not being redacted. I noted that Windows does not ship with a whois command. And you can get various third-party alternatives, and you can try those. However, there is a solution that works on all operating systems. And the solution entails what is known as domain name hacking, something that we should quickly discuss. Domain name hacking occurs when you use a domain to sound like something else. In other words, you want an abbreviated YouTube and you register something in Belgium. You already have the BE from Belgium, and you can use an abbreviated form of YouTube. The particular example that I am referring to is a server with the name who.is. Clearly, the idea is that you should not read it as who.is in the Iceland domain, but that you should read it as whois. Now, this particular server or service is one that will try and sell you something. If you look up a name, it will suggest alternative names that look very similar. And yes, that's how it makes its money. However, I do find it a useful tool when I need to use it. And one simply goes to the website who.is and proceed from there. Who.is seems to suggest that it is in Iceland, because .is is Iceland, but it is not in Iceland at all. One of the notions that we've been discussing for the entire duration of this video is that of a zone file, but we have not yet looked at a zone file, so it's about time for us to do so. So here I have a little zone file to serve as an example. I have not checked that the various values make sense, but it should still illustrate the notions quite clearly. This particular zone file is in the format that is used by Bind, that is the Berkeley Internet Name Daemon, which is probably the best known name server software that is used on the internet. So what we can start with is to see that there is a time to live indicated in the top there, and that is the number of seconds that entries from this particular zone file may be cached by other servers. Then the next entry in this file is the SOA entry, start of authority. And the start of authority contains a number of interesting values. One thing to point out there is the @ which is this domain, and we will see quite a couple of uses of the @ as we move down. However, for our purposes here, it is not particularly interesting, and here we simply have the name of this server that we are setting up, so it's the name of the name server, and that is followed by the email address of whoever is responsible for this server. So what we do have here is that there is the email address, and there is something rather interesting in it, in the sense that you don't see an @ The very first full stop is simply replaced by an @ by Bind. Now, clearly, if your email address happens to be a.b at something, it won't work. You have to pick an email address without a full stop in it. One other thing to notice here is that whatever name we use, it tends to end with a full stop. So this is one of the few places where you do use that full stop at the end of a domain. Then this SOA record continues with a couple of values: the so-called serial number, the refresh number, the retry number, the expire number, and the minimum time to live field. These bottom four fields are all specified in seconds, and we will talk about what they mean just now. Let's just look at the serial number. So in principle, the serial number is a value that simply indicates the serial number of this particular file. And what is indeed possible is to start at 1 and then go to 2, and if you edit it, go to 3, and so on. And the reason why you have serial numbers is so that the secondary name servers can see, you've updated your zone file, and I only have version 2 of your zone file, and the primary name server suddenly is serving version 3, so I hence have to get the new value. There's a fairly standard practice in networking where you use the date as the basis for your name server serial number. So what this means is, if we look at that number there, you will see that the first 4 digits look like a year, and they are indeed a year. And then the next 2 digits specify a month, and then the next 2 digits specify a day, and then the next 2 digits specify the version of this file on that particular day of that particular month of that particular year. So this is one way in which you can keep a record of exactly when you made a change to the zone file. And by definition, because dates increase and months increase and so on, it will always be a bigger number when you create a new version of this file. As we said, this is for the secondary name servers to realize that a new zone file is available. Now, they can check for the serial number of a zone file, but they are also prompted by modern software. When you change the zone file on a primary server, the secondary servers are prompted by this. It's quite interesting to look at the serial numbers of various zone files, because this is a fairly standard convention, even though it is not mandatory at all to specify your serial number like this. And this, to some extent, shows you whether the networking people who have set up this zone file know the culture of networking, or whether they just use a number. However, there are also other reasons why they may use special values. The next entry that we see here, the refresh time, again specified in seconds, tells the secondary name server how long it can keep on serving entries that it has without needing to check the primary server to see whether an update is available. So if your domain tends to change quite rapidly, then you will have a very small value in there so that the secondary name servers can remain up to date. However, if in the zone change hardly ever, then you can use a fairly large number there, and the secondary name servers will mostly be up to date. The next number, the retry number, is also a number in seconds that specifies how long a secondary name server should wait before checking for the serial number if it could not get this number from the primary server when it queried it. The next number, the expire number, is the number of seconds that a secondary name server should keep on serving names for this domain until it should give up if it can't communicate with the primary server. So use a pretty large number there, that if your primary server is down, it doesn't mean that very soon your secondary servers will quit. They should go on working for quite a while. However, if they have not been able to contact the primary server for a long time, it clearly indicates that something is amiss, and it is necessary for them to perhaps stop working, rather let the query fail than go on serving something where it has lost contact with the primary server that may actually be updated every once in a while. And then the final value in this example is the minimum time to live. Now, this is a strange time to live. This is a negative time to live. So the idea is, suppose you query something and you don't find it. So it's a negative response. You get an answer that says this name does not exist in the domain. For how long can you assume that it does not exist? And specifically for other name servers that now have found this information that the name that you were looking for doesn't exist, how long can you tell other parties that this name doesn't exist before you should rather come back to the primary server and see whether the name does not exist in the zone file at this stage. All the other entries in the zone file consist of a name followed by IN, simply says this is an entry for the internet. So name services were also used for other networks. You won't find any other examples nowadays, so IN is almost a constant, it's a given there. And then you will find the type of entry. Now, we already said that if you see an @ there, then it means that you are talking about this domain, the domain for which this zone file is being used. And what this tells you is that this particular server, the one that you also mentioned up there, happens to be a name server for your domain. So it is a name server entry for the local domain. Then the next three values that you see here are names of computers. And what you can see is, or how I know that they are names of computers, is they all have an A record, an address record, and you will see that the address entry is followed by an address. So if someone were to look up Arthur in my domain, then they would be told by my server that that 10.1.1.1.1 is the answer to the query. Similarly, if they were to query my server and they were to ask about Lancelot, then they will get the answer 10.1.1.2, and if they were to query my server for Quixote, then it will get the answer that the address is 10.1.1.3. I, for some reason, also wanted to give that Quixote machine a different name, and this different name that I used was Don. And what I said here is that Don is simply a canonical name, a C name, for the machine known as Quixote.example. So C names, canonical names, are used to define synonyms. I wanted to give you an example of an IPv6 address. This one doesn't make sense, but let's use it as an example. Anyway, here I made an entry in DNS for localhost. Now, localhost would normally be your own machine, so there's no reason to go and look up the address of your own machine in a DNS system. What this illustrates is the type AAAA record. You can sort of see that it is 4 times as long as an IPv4 address. This is an IPv6 address, and you can see the different notation that we use for the IPv6 address. We will talk about that later on when we get to the appropriate point. Here I am giving the names of the mail servers for my local computer or my local domain. So the @ means my domain, yet again the domain for which the zone file is created. And then there is an MX entry. The logic of the MX entry is you may not want to send mail to your domain to the usual machine. Maybe if it's a laptop, you may be switching it off and on and off and on, and it may not always be online. For mail service, you really would like a machine that is online all the time. So you may be redirecting your mail to a different server, and in this particular case, the server to which I am directing my mail happens to mail.example. I also, next to this MX entry, included a priority, and the priority is 10, and the lowest priority will take precedence. So what you can see with my alternative email address, MX address, that priority is 20, and as also suggested by that particular name, this is intended as a backup server to receive my email if the primary email server is not available to receive mail. Often you will use these entries to redirect mail from wherever out on the internet, not to the domain at which they are addressed, but rather to send them to some machine where you can do spam filtering. And that is one reason why you may have a central mail repository, in addition to the fact that you want a machine that is up all the time, that is not only up when you are using it, as an example. And this is a complete example of a zone file for a particular domain that I've not really specified. It seems to be for example.com. That's certainly what it suggests. What I also could have done here in addition is to have added subdomains, and then to, in other words, provide the name of the subdomain there. Suppose I wanted to call it sub. Then I could have had another NS entry, a name server entry, that would point to whichever machine is willing to resolve names for my subdomain. So these entries that I've used here, the NS, the A, the C name, the AAAA, and the MX, and now also NS again, is not a comprehensive list at all, but they are the most popular ones. They are the ones that are used most often, and this should suffice for our purposes. In order to fully configure my name server, I also have to create a reverse name lookup file where I would specify the addresses and tell the name server to which names do they map. So it is one additional step that I have to complete before I can launch my name server. I also have to configure my name server to tell it from whom it should accept queries. Finally, I should also tell a name server whether it's the primary one, in which case I will provide it with a zone file, or whether it is a secondary name server, in which case I have to tell it where the primary name server is, and I also have to give it authority. I have to authorize it to transfer the zone from the primary server to the secondary server. Just to emphasize the point, when you do transfer this entire file's contents from primary server to a secondary file server, it is known, as one would expect, as a zone transfer. As always, it is good to experiment a little bit. What we are going to do now is to look at a couple of domains and specifically look at the start of authority entries. So we want to see whether they use the appropriate conventions and so forth. As our first example, let's look at the University of Stellenbosch, sun.ac.za. You can see that we have a lot of information about name servers and so on flashing by. But before we got that, we did get an answer. And the answer that we received there, the serial number, you can see that they seem to be using the convention that we mentioned previously. So it seems as if their zone file, primary zone file, was updated in 2021 in April, on the 5th of April, and they've actually updated it 96 times on that day. Now, whether that is true, whether they are really using the convention, that is up to you to figure out. Maybe check early in the morning on a day and see whether they have a smaller number there. You can also see that they say who is responsible for this DNS admin, and you can yet again see an email address, but with a full stop that should be replaced with an @ There is the name of the primary name server, and you can see the refresh rate, in other words, how many seconds a secondary server is allowed to cache values without querying 7,200 seconds. That translates to 2 hours. If a secondary server is unable to get the value of the serial number, then it should try 3,600 seconds later, that is 1 hour later, and a secondary server should stop resolving names after so many seconds, which translates to about 14 days, 2 weeks. If a secondary server was unable to talk to the primary server, after 2 weeks, give up. And then the default time to live, in other words, the amount of time for which another server can cache an answer that it received from this particular server, so many seconds, and that translates to exactly 1 day. So if you are using it from your ISP and you are accessing a computer at Stellenbosch University, then for 1 day your name server is allowed to use whatever address it got, and it is not necessary for it to check again. So let's look at another example. What we can do here is to look at, let's say, Google. Again, we get a lot of information and flashing past about name servers and so on. You can look at those later on. The serial number, it seems Google is not using that particular method that we used previously. The refresh, in other words, the time a secondary name server is allowed to continue without checking, is 900 seconds, and that translates to only 15 minutes. So they want their secondary name servers to be updated very regularly. If a secondary name server cannot get the version number from the primary server after 15 minutes, it should try again. We just saw with the University of Stellenbosch, they said wait an hour, and then you try again. And then expire, in other words, a secondary name server should stop working if it has not been able to talk to the primary server for 30 minutes. In the case of the University of Stellenbosch machine, a moment ago, we saw that it was allowed to go on for 2 weeks before it would give up. And then your computer, your name server, is allowed to cache a value for 60 seconds, for 1 minute. And then it has to go back to Google servers to get a response. So you can see this is a very, very different set of values from what we had at the University of Stellenbosch. Let's move on to another option, and in this case what I want to do is to look at Microsoft.com. Remember, we are still set up to look at SOA entries, and with Microsoft we yet again get all these name servers that could provide us with better information, but the information that we got is the primary name server, and here amazingly the serial number is 1. That seems to indicate that this is the original name server that Microsoft has ever used and that they've never changed it. I'm not sure, this doesn't make sense. They're using a different set of rules clearly, because secondary name servers will generally update when they see a new serial number. We did, however, say just now that on modern servers, when the primary name server is updated, it will inform the secondary name servers, and the secondary name servers will then be able to download the file to do a zone transfer. the refresh, so how long a secondary name server is allowed to continue without checking with the primary name server, 1 hour. And if a secondary name server cannot get the version number, it should check with the primary name server within 5 minutes again. Then the expire, in other words, the minimum time before the name server, the secondary name server, will give up. Microsoft says secondary name server will keep on working for 28 days. Compare that to the 14 days for Stellenbosch University and the extremely short time for Google. And then Microsoft says if you have a name in the Microsoft domain, you can cache it, you can keep using it for 5 minutes, and then you should check back. So yet again, gives you this range of values, very, very different assumptions. And what you should really do is to go and look up the SOA entries of a different set of parties at other universities, and then try and figure out what their reasons behind these choices are. Do they change names very often and therefore they don't want you to use a secondary name server for a long time? Do they change addresses very often and that's why they don't want you to cache an address for a very long time? And so on. Play around, think a little bit about what these values mean so that when you do look at an SOA entry, you can try and make some sense of the type of environment that they see themselves as working in. Now, we should also say that many systems, many commercial systems, have network administrators who do not understand these values at all. This will probably not be true for your Microsofts and your Googles, but many administrators will set up these values to something that they saw in some example without thinking about it. So this is one of the areas where people very often administer a network and they don't really know what they are doing. As I said previously, one way of checking whether they are familiar with the culture at least is to check that serial number, which generally speaking one would expect to be the date and 2 digits for the version or the number of changes on that particular day. As a final remark, before we conclude this video, there is an app that I find rather useful, and I recommend that you look at it or other equivalents. This is Landroid, which is available for Android. I assume there are similar products available for Apple, and you will find something suitable if you are using an Apple phone. What the app does is it simply performs the functions, the basic functions that we've been looking at. So as an example, we have been playing with the DNS. And if you want to resolve a DNS name, then you can simply enter the domain name there. You can see the fully qualified domain name, FQDN abbreviation that we've not previously mentioned. If we want to look up mo.org.za and I say go, you should find or you should get a result very quickly. And it is arguably too hard for you to read, but it does make the point that this sort of functionality is available in a simple app. Looking through the other information or the other options that we have a whois option there. We have a couple of IP calculations and so on, things that will be useful later in our discussion. For the time being, do look at these apps, especially something like this, which is free of charge, and try and use them as well so that you experience the output provided by different sources, different devices, Windows, Linux, and your cell phone. This video was a journey through the domain name system, the DNS. And as you are aware, the DNS is at the very heart of the internet. Without it, the internet would not have been able to reach the heights that it has reached. Our journey took us through the technical operation of the system. It, amongst others, illustrated how local autonomy and redundancy achieve the design goals of the internet. Design goals that we should also keep in mind when we look at other protocols that underlie the internet. We spoke about the notion of delegation as the mechanism by which a subdomain is added, and how a registrar would add your name to a registry if it is possible to do so, and possibly after payment of the necessary fees, would add your name to that registry, your domain name that you want, and set up its zone file, its registry, and point to your name servers that you should set up when you configure the domain initially. We also spoke a little bit about the reasons why a certain name would be acceptable or would not be acceptable in a given context. Amongst others, in the South African context, we saw that ZATNA, as the controlling authority, has the power to decide which second-level domains are introduced, and as long as they enforce that policy, I cannot simply go and register a second-level domain. Whereas in other countries, often you can register a name in the second level of the DNS without any problems. So there are reasons, there are pros and there are cons for these various approaches to doing things. To illustrate who is allowed to register a name in the domain name system, the case of a certain Mr. Nissan, who registered Nissan.com many years ago for his tiny computer shop, perhaps illustrates the concept best. While the giant motor manufacturer with the same name has been trying to get that domain for a long time, that motor manufacturer has been unable to do so because Mr. Nissan had all the reasons in the world to register that name for his little computer shop. There are many more aspects of the domain name system that really warrant discussion. However, this video is already extremely long and we have covered the major topics. It is time for us to move on to the next application layer protocol.
Cctlds.